Well, at this point you may ask me, shall I think in terms of ensemble, or shall I think in terms of tracing over entangled subsystems when we talk about density operators? The answer is it's okay to think both ways. So they are equivalent. The two approaches, the two sort of mental pictures are to some extent equivalent, and it is your preference. It's very contextual. It depends what kind of problem you're facing. Sometimes it's easier to think this way, sometimes it's easier to think the other way, and it doesn't really matter because the two approaches are equivalent in the following sense that if you are given a density operator that is associated with a given system, I call it system A, you can, let me just write this operator using the spectral decomposition. So you can always decompose your density operator, write it as follows. So it's P sub k, AK, AK. So now, when you look at the spectral decomposition of your density operator, then the obvious mental picture you may have is that it represents ensemble, right? So you may think about a source that generates state A1 with probability P1, or it can generate state A2 with probability P2, and in general it can generate state, say, AR with probability PR. So that's a very natural way of thinking about this expression. However, it is also possible to think about this density operator as the result of tracing over some external subsystem that may be associated, may be entangled with the system A. Well, indeed, if you recall our discussion of the Schmidt decomposition, that you can almost immediately guess what kind of state should we have of the combined subsystems of the combined system A plus B. So the state psi that let me just write it for you. Sum over k, square root of pk, a k tensor bk, where bk are vectors taken from some orthonormal basis in the subsystem B. Now, when you look at this expression, you can see that it will generate this particular ensemble if you perform the measurements on subsystem B in this basis. Well, indeed. So if you choose this basis for your measurement, so if you get, say, outcome 1, which means that you start projecting on B1, therefore the corresponding state of the A system will be A1, and that happens with probability P1. So you can also, with probability P2, project on the tensor product state of the type A2 on this system, B2 on this system. So that's the outcome 2. And all the way to PR. With probability PR, you can project on state AR tensor BR. So this is when you get outcome R. So when you look at the relative states here associated with subsystem A, you can see right away that this is A1 with probability P1, this is A2 with probability P2, and so on and so forth. So essentially, from the perspective of system A, you generate this particular ensemble. So you perform the measurement in that particular basis in subsystem B, and you generate this ensemble. Then, of course, if you don't want to do it this way, you can also do the partial tracing, because you don't have to really perform this measurement to see this equivalence. You don't have to do anything to subsystem B, and you can see that by taking a partial trace of the density operator associated with the combined system. So that's your projector on state side, right? So that's the corresponding density operator, which you can write as a sum over k and l. That would be a square root of pk pl, and then I will have operators ak BAL, tensor BK BL here. So that's my density operator of the whole, and in order to get my density operator associated with subsystem A, I have to trace over subsystem B. So essentially I'm just doing nothing to this part and I'm applying trace to this part here. And when I apply trace to this part here, you can see that this is going to be equal to the scalar product BL BK. Remember this formula. If I have a trace over the operator which is of this form, that is equal to the scalar product BA. That's a very convenient thing to remember. So now those are orthogonal vectors, right? So essentially then when we do this tracing, we get this density operator. So when I just do the trace over B, I get the density operator. So you don't have to really perform the measurement. The performing measurement was just one way of thinking how to generate this ensemble. In fact, you should have this intuition that it doesn't really matter what I do to state B. It shouldn't affect the reduced density operator of subsystem A, right? Because those things could be just miles away. And so the statistical predictions that you are going to make here should not depend on what you are going to do to this system, honestly. So because otherwise we would just think very carefully, because it's actually quite a subtle point. Otherwise, we would be able to construct a device for instantaneous communication between B and A. If doing something to B had sort of effect on the reduced density operator, then changing the reduced density operator here means different statistics here, which could be sort of detected by appropriate set of measurements. So it doesn't really matter. You can measure B, you can throw it away, you can kick it, you can bite it, do whatever you want to be. That is not going to affect the reduced density operator. So once you are in this particular state, do what you want to be. It's not going to change anything. So in particular, one thing that is worth adding is that this purification, therefore, is not unique, right? Because if I say that do whatever you want to this state, one thing I can do, for example, do whatever you want to subsystem B. So one thing I can do, for example, I can just apply a unitary operation. So I can take the state, the purifying state, where shall I write it, perhaps here, and construct a new state, psi prime, which is acting with some unitary on subsystem B. So what this is going to do essentially is going to affect only this part of the joint density operator. So this operator here will be modified by U and U dagger on both sides. So as you can see, it's not going to affect the partial trace, because if you do the partial trace with those modified operators, you still get you still find them orthogonal. You still, after the reduction, get the same density operator. So the statement is the purification is not unique. Purification is actually up to the unitary operation on the external subsystem.